Chapter 2 Science and Measurement. On August 21st, 2003, on a specially built hill in Irvine, California, 6 adults climbed into cars with no motors and rolled downhill. In the extreme gravity race, the cars reached speeds of up to 60 miles per hour as they raced down the hill, using nothing but gravity for energy. The 6 cars represented 6 fiercely competitive design and engineering teams. The race featured teams from 5 different automakers. Each team had created the slipperiest, low-friction car they could using carbon, fiber, titanium, and many other high-tech materials. 2.1 Inquiry and the Scientific Method. Scientists believe everything in the universe works by a set of rules called natural laws. Everything that happens everywhere obeys the same natural laws. Unfortunately, the natural laws are not written down, nor are we born knowing them. The primary goal of science is to discover what the natural laws are. Over time, we have found the most reliable way to discover natural laws is called scientific inquiry. Learning by asking questions is called inquiry. Figure 2.1. An inquiry is like crime investigation with a mystery to solve. Something illegal happened and the detective must figure out who did it. Solving the mystery means accurately describing who did what, when they did it, and how. The problem is that the detective never actually saw what happened. The detective must deduce what happened in the past from information collected in the present. In the process of inquiry, the detective asks lots of questions related to the mystery. The detective searches for evidence and clues that help answer the questions, and eventually the detective comes up with a theory about what happened. To be accepted, a theory must pass 3 demanding tests. First, it must be supported by enough evidence. Second, there cannot be even a single piece of evidence that contradicts the theory. Third, the theory must be unique. If 2 theories both fit the facts equally, you cannot tell which is correct. When the detective arrives at a theory that passes all 3 tests, he believes he has solved the mystery by using the process of inquiry. In science, the only way to know you are right is to compare what you think against real evidence. However, what types of evidence qualify as scientific evidence? Do feelings or opinions count as scientific evidence? Does what other people think qualify as scientific evidence? The answer to both questions is no. Both evidence is so important in science, there are careful rules defining what counts as scientific evidence. Scientific evidence may include numbers, tables, graphs, words, pictures, sound recordings, or other information. The important thing is that the evidence accurately describes what happens in the real world. Scientific evidence may be collected without doing experiments in a laboratory. For example, Galileo used his telescope to look at the moon. He recorded what he saw by sketching in his notebook. Galileo's sketches are considered scientific evidence. Scientific evidence must be objective and repeatable. Objective means the evidence should describe only what actually happened as exactly as possible. Repeatable means that others who look the same way at the same thing will observe the same results. Galileo's sketches describe in detail what he actually saw through the telescope. That means that the sketches are objective. Others who looked through his telescope saw the same thing. It is important that scientific evidence be clear, with no room for misunderstanding. For this reason, scientists define concepts like force and weight very clearly. Using the scientific definition is similar to the way you already use the word, but more exact. For example, your weight in science means the force of gravity pulling on the mass of your body. Scientific theory is a human attempt to describe a natural law. For example, if you leave a hot cup of coffee on the table, eventually it will cool down. Why? There must be some natural law that explains what causes the coffee to cool. A good place to start looking for the law is by asking, what is it about the coffee that makes it hot? Whatever quality creates hot must go away or weaken as the coffee gets cold. The question of what causes the hot and cold puzzled people for a long time. Before 1843, scientists believed a theory that heat was a kind of fluid like water that flowed from hot or cold objects to colder objects. They called this fluid calorie. People thought that hot objects had more caloric than cold objects. When a hot object touched a cold object, the caloric flowed between them until the temperatures were the same. The caloric theory explained what people knew at the time. However, a big problem came up when people learned to measure weight accurately. Suppose caloric really did flow from the hot object to a cold object, when an object should weigh more than hot compared to its weight when cold. Experiments showed this was not true. Precise measurements showed that objects have the same weight, hot or cold. The caloric theory was soon given up because it could not explain this new evidence. Scientists are always testing the theories we believe against new experiments and new evidence. One of two things can happen when new evidence is found. 1. The current theory correctly explains the new evidence. This gives us confidence that the current theory is the right one. Or 2. The current theory does not explain the new evidence. This means there's a new or improved theory waiting to be discovered that can explain the new evidence as well as all the old evidence. And hypotheses. Based on observations and evidence, a good detective evaluates many different theories for what might have happened. Each different theory is then compared with the evidence. The same is true in science, except that the word theory is reserved for a single explanation supported by a lot of evidence collected over a long period of time. Instead of theory, scientists use the word hypothesis to describe a possible explanation for a scientific mystery. Theories in science start out as hypotheses. The old explanation that heat was the fluid caloric was an incorrect hypothesis, one of many leading up to the modern theory of heat. The first hypothesis that heat is a form of energy was made by a German doctor, Julius Mayer, in 1842 and confirmed by experiments done by James Joule in 1843. Energy has no weight, so Mayer's hypothesis explained why an object remained unchanged whether it was hot or cold. After many experiments, Mayer's hypothesis that heat was a form of energy became the accepted theory of heat as we believe today. Figure 2.4. A scientific hypothesis must be testable. That means it must be possible to collect evidence that proves whether the hypothesis is true or false. The requirement means not all hypotheses can be considered by science. For instance, has been believed at times that creatures are alive because of an undetectable life force. This is not a scientific hypothesis because there is no way to test it. If the life force is undetectable, that means no evidence can be collected that would prove whether it exists or not. Science restricts itself only to those ideas which may be proved or disproved by actual evidence. Scientific method. At first, humans learned about the world by trial and error. Imagine a small child trying to open a jar. She will try what she knows, biting the lid, pulling on it, shaking the jar, dropping it, until by chance she twists the lid. It comes off. She puts it back and tries twisting it again, and the lid comes off again. The child learned by trying many different things and then remembering what works. It takes a long time to learn by randomly trying everything. What is worse, you can never be sure you tried everything. The scientific method is a much more dependable way to learn. The scientific method. 1. Scientists observe nature, then develop or revise hypotheses about how things work. 2. The hypotheses are tested against evidence collected from observations and experiments. 3. Any hypothesis that correctly accounts for all the evidence from the observations and experiments is potentially correct theory. 4. A theory is continually tested by collecting new and different evidence. Even one single piece of evidence that does not agree with the theory will force the scientist to return to step 1. The scientific method is the underlying logic of science. It is a careful and cautious way to build evidence-based understanding of our natural world. Each theory is continually tested against the results of observations and experiments. Such testing leads to continued development and refinement of theories to explain more and more different things. The way people came to understand the solar system is a good example of how new evidence leads to a new and better theory. Please pause here and answer these questions.